Welcome back after the study break. Hopefully you've been able to catch up and catch up with all your work. So what we're going to be talking about now is linear algebra and linear systems, because often in reality what you actually have is you have a series of equations. So if we have a graph like cost and number of units, what you might have is an equation for the cost of, if I'm going to be a factory and I'm going to be building lots and lots of things like cars or things like that, there might be a cost line like that. So the more cars that I build, the cheaper they get. So that's cool. So there'll be an equation for that. Y is equal to C1x plus, or K1x plus C. And there may also be what you can charge or demand. And at some point in here there will be a point where both these lines cross, and that will be your point of maximum profit. For some reason economists love doing this stuff as well. Or what I was doing in my research is I was looking at a model of the atmosphere. So what we have is we have the sun, it's shining out, and I had three layers of the atmosphere. I had the surface, I had the troposphere, and I had the stratosphere. And I was looking at the amount of energy being absorbed by each layer. So the temperature at this layer is going to equal the amount absorbed plus the amount going down plus the amount coming back up, because someone's going to reflect. And so for each of these layers I've got amounts going down, and I end up with three equations. And I want to find out when all three of these equations are true at the same time. They've got me masters that, so hey, can't be all bad. So anyway, so how can I do multiple equations? And the answer is we can actually write up multiple equations. 3x plus 2y plus z equals 6, and so on. Now if we were to draw graphs, let's draw x and y. If I have two equations, x plus 2y equals 6, 2x minus 3y equals 8, I'm just making up equations here. If I actually have equations like this, if I have two lines, I can find a point. So if I've got two unknown variables, as a general rule I can find a point where they meet. Sometimes these lines will never meet. If they're parallel, they will never meet. But as a general rule, if they're not parallel, at some point they will meet and I can find a value. But what happens if I get a third value in there, plus 2z? And now all I can do is I can figure out, if I got two unknowns, two equations, I can figure out a point. If I got three unknown, two equations, I've got a line or where it can be true. If I've got four unknowns and two equations, I've got an area. Anyway, besides the point, let's get back to what we're doing. So how can we represent this? And often what we can do is we can represent these equations in the form of a matrix. So what I can do is if I have an equation like 2x plus 3y equals 6 and 3x minus y equals 9, I can actually write these as a matrix. I've got two. Let's try that again. I've got 2x's plus 3y's equals 6. I've got 3x's negative y equals 9. Isn't that cool? And as you can hopefully see, these you can make very, very big. And in some systems we're using even hundreds of equations with hundreds of variables. So this is actually, believe it or not, a powerful tool. And in fact, it's so powerful, we have actually gone out and invented or written computer language dealing specifically with matrices, and that's called MATLAB. And there's also a few clone versions of it as well. So where would these matrices actually, where would these linear systems actually turn up in reality? Well, one system is modelling the economy. If you look at an economy, you've got dollars going in, you've got taxes, you've got all sorts of stuff. So an economy can be modelled as like 100 equations with 100 variables. And actually nowadays they actually use much bigger models than that. Other things are things like cars. If you've got 4 wheels, so those are springs and these are the wheels. Each of these wheels in a car will affect the other wheels. So each wheel is going to have an equation. Z1 plus Z2 plus Z3 plus some constant equals velocity. So each one of these wheels will have its own equation. So to find out how fast the person, if I'm sitting in my car, how fast I'm bouncing up and down and what's going on, I have to solve all 4 of these equations simultaneously. Actually, cars, you often have to do 28, 29 equations. Or if you're doing resistor networks, if you're dealing with resistor networks, there's one resistor, there's another loop, we'll put in a battery over here. If you're doing things like Kirchhoff's loop laws, and the electrical engineers will learn to swear and curse at these, how can you work out the voltages and the currents going through each of these elements? And the way you do is you set up loops. So there's going to be loop 1, loop 2, loop 3, and each of these is going to be a simultaneous equation. And then, so you can end up with simultaneous equations with huge amounts. Or another one, this is a really simple example, which the mechanical engineers might be doing. If you're building a truss frame, like a roofing truss or something, you're putting force on there, how can you figure out all of the forces going everywhere? And what you'll do is each point here, you can say this point here, we've got force up there, we've got force going that way, we're going that way. You can set that up as an equation. You can set up the forces there as an equation, the forces there, there. So we're going to have 1, 2, 3, 4, 5, 6 equations. And if we've got 6 variables, then we can work that out totally. We can work out every force by using matrices. So anyway, lots of people, computer programmers, things like that, often what you'll do is you'll set up a CAD program or something like that. Or if you're actually dealing with imaging, you'll set up a large matrix. You'll actually break up a picture into hundreds and hundreds of elements. I mean, it was the old thing, 640 by 480 was the old imaging standard for a while. Nowadays it's 4000. And you're going to store that as a matrix, believe it or not. So anyway, lots and lots of things, don't worry about it. When we're using CADs, everything's stored as a matrix. When we're dealing with resistor networks, hydraulic networks, compressed air networks. So the question is, we have lots and lots of matrices. How can we solve matrices? Well, if we've got a simple matrix, something like 6x plus 4y equals 3, 4x minus 2y equals 7, just making up numbers here, we're not going to solve this. What we can actually do is, one way of doing this is we can use Cramer's equation on it. And you should all know Cramer's equation. Now, Cramer's equation, yep, works. For some reason, engineers internationally like it, but Cramer's equation is simple and easy to use and it's simple enough to understand when you're dealing with small matrices. If you're dealing with 2 by 2s or possibly even 3 by 3 matrices, yeah, you can deal with that. You can write computer programs that deal with it. However, once you start getting bigger, say 6 by 6, 10 by 10 matrices, the computational power required to solve a system of simultaneous equations using Cramer's equation just blows out. And when you get to really big arrays, 100 by 100, you just sit there all week just waiting for an answer. So there's another system that you're being taught, which is Gaussian elimination and Gauss-Jordan elimination. And basically you set this up as an 6, 4, 3, 4, -2, 7. You set that up as an array or as a matrix, and then you will solve that until you've got something like I'm just making up numbers here, don't quote me, 0, 1, -6. You're basically going to apply the elimination process. And when you're dealing with bigger problem arrays, this is actually a much more efficient system. In this course, it's doubtful we're going to get you to actually solve much more than the 3 by 3 or even 4 by 4 array by hand. In reality, once the arrays get over about 3 by 3, we just stick them in MATLAB and use MATLAB to solve it. And what MATLAB does is it uses Gauss-Jordan. It doesn't use Cramer's rule because too heavy on processing power. It will use Gauss-Jordan elimination to work out all the problems, solutions. So anyway, yeah, you probably don't like the idea of matrices, you don't like the idea of vectors, you don't like the idea of systems of simultaneous equations, but they are very useful for describing when lots of things are connected. Even though you've got lots of independent variables, they are still related. The results of them still relate to give you some measurement, like seeing a car seat with lots of car tyres. So you will be seeing these. So, yep, yeah, you'll be seeing these a lot. And if you're doing a lot of work, you'll be using MATLAB a lot. So good luck. We'll see you in the next one. And yeah, don't forget to do the problems in the workshop.